Good morning, students. Today we are going to discuss about design of cooling tubes in the transformer. So we have the rating 250 kVA, 6600 watt by 400 volt. Three-phase core type transformer has a total loss of 4800 watts. Okay, on full load. This is nothing but full load loss. Correct. So then the transformer tank is given as 1.25 meter height and 1 meter length and 0.5 meter width. Okay, sometimes all the three dimensions together is given as 1 by 0.5 by 1.25. Okay, so we have to consider L, H and with L, W and height, like that. So we are going to design tubes for this transformer tank. Here the average temperature is limited to 35 degrees Celsius. That is, temperature rise is given as 35 degrees Celsius. The diameter of the tube is 50 mm and are spaced 75 mm from each other. Even though these values are not given, dia and spacing between the conductors are not given, means we have to take assume these values. These are the standard values. Okay, the average height of the tube is 1.05 meter. And then improvement in cooling is 35% due to tubes. So even if it is not given, the improvement in temperature is not given, we can assume this as 35 degrees Celsius, right? 35%, correct? 35%. Sometimes they'll give the improvement. Okay, based on that we have to put the value. So sometimes 40% improvement, like that they will give. If it is not given, we can take it as 35. Okay, in this problem it is not given, so I have taken it as 35 35% improvement. Okay, so these are the given data. So Q is equal to 250 kVA 3-phase transformer and full load loss is given, height of the tank, length of the tank and width of the tank, and theta is equal to 35 degrees Celsius, diameter of the tube 50 mm, length of the tube 1.05 mm. Correct. Then we are having only two formulas. We are going to form the formulas. Okay, first one is number of the tubes is equal to total area of tubes by area of each tube, and then theta is equal to full load loss divided by loss due to dissipation. The dissipation occurs in the tank by convection as well as radiation. Okay, but in tubes, no, only by convection only heat dissipation occurs. Please remember that one. And for convection, no, we will have this value 6.5 watt per meter square. Watt per meter square degree Celsius. For radiation, the values is 6 watt per meter square degree Celsius. Okay. Now this is the consider this is the surface area of the tank. Only lateral surface are responsible for the heat dissipation. So front face, back face, two side faces are included here. Top and bottom are usually neglected. Okay, so let surface area of the tank is ST. Correct. We are going to find out the formula for ST. So first, front face LT multiplied by HT. It looks like a rectangle, correct? LT and HT. We have front face and back face, so I have provided here 2 LT and HT. And then side faces, it is nothing but width of the tank and multiplied by height of the tank. So we have two faces, so 2 into WT. I have taken 2 HT as common, and remaining is LT plus WT. If I substitute all the values here, I'll get 3.75 meters square, which is the surface area of the tank. Then we can take surface area of the cooling tubes, no, as X into ST, because we are going to place the cooling tubes around the surface of the tank. Hence, we can take surface area of the tanks as X into ST. Then area of each tube. Tubes looks like a cylinder, correct? See here. Now, if the circumference of the circle is 2 pi r, in terms of dia means pi dt. If you take the entire length, then the surface area, which is responsible for the dissipation, will get, correct, LT. So area of each tube is pi dt LT. Now NT is equal to XST, surface area of the entire tubes divided by area of each tube. Here, no, X is not known, the remaining values are known. ST, we have found it out. DT, it is given in the problem. LT is also given in the problem, correct? So our aim is to find out X only. This x can be found out from this formula. Theta is equal to full load loss divided by loss due to dissipation. Clear? So now loss due to convection and radiation in tank. The dissipation occurs because of the tank as well as tube. Correct? First we will consider loss due to convection and radiation in tank. Correct? So 6 plus 6.5 watt per meter square degree Celsius. So total loss, this is for per meter square, that is for 1 meter square we have 12.5 watt per degree Celsius. For the entire surface means 12.5 into St watt per meter watt per degree Celsius. Okay. Now we'll see the loss due to dissipation in tubes, which is due to only convection, and it has the improvement of 135%. Correct? So 6.5 convection, no? So 6.5, 135% of improvement. So I have put 135 by 100 multiplied by 6.5 is for 1 meter square. Correct? For the entire surface means, for tube entire surface area is, we have considered as XST. Okay. So if we simplify this, we'll get this as 8.8 XST. 8.8 XST. Okay. Now we have to combine both tank as well as tube. Correct? So total loss due to dissipation of in tank and tube. Okay. So what is the value? 12.5 ST plus, this is in tank. Correct? Then 8.8 XST. Correct? We have to substitute in theta. So theta is equal to full load loss, we know 4800 divided by loss due to dissipation, this is in tank, plus 8.8 XST, this is in tubes. Okay. We know ST value, here also we know, only theta also known, all the variables are known, only one unknown is here, X only. Correct? We have to find out X value. So theta is equal to now 4800 divided by 12.5 into S, the value of ST is 3.75. Correct? 3.75 meter square. So 3.75 meter square plus 8.8 into X, 3.75 meter square. Theta value, it is given. Correct? 35 degrees Celsius. So if we solve this, we will get X value as 2.7354. So 2.7354 is the X value. Now we can solve the number of tubes. What is the formula? Again I remember this, XST divided by pi dt LT. Okay. So now X value is 2.7354 multiplied by ST is 3.75, right, divided by pi. DT value, see here everything is in meter square, DT and LT will be in mm. Correct? That should be converted into meter. Okay. So DT, dia of the tube is 50 mm. Correct? 50 into 10 power minus 3. Even if it is not given, it is a standard value, you have to assume this one. And then length of the tube is 1.05 meter. It is given in already in meter, so no need any conversion. So 1.05. Solving this, we will get NT is equal to 62.206. So we can take number of tubes as 62. So this is the minimum requirement for the dissipation or improvement in cooling. Correct? Number of tubes to be provided are 62. So these tubes are to be placed around the tank. Correct? Now the tank, this is the surface. Correct? Now length is 1 meter, which is nothing but 1000 mm, and then width is 0.5 meter, which is nothing but 500 meter. So along the width and length, how many tubes can be provided. Okay, here see this length as well as here itself we can provide the number of tubes here as well as here. Here no, length of the tank is 1000 mm, width of the tank is 500 mm. So initially we leave 75 mm. Okay, so 1000 minus 75, 975, and 500 minus 75, 425. Then we'll find out how many tubes can be placed along the length. Okay, so now NT is equal to 975 by 75. This is along the length only. Okay, so we'll get 12.33. So we can keep approximately, so number of tubes can be approximately, we'll keep 12 tubes along the length. Similarly, number of tubes along the width means 425 divided by 75, which comes around 5.67. So I'll take this as 6 tubes can be placed along the width and 12 tubes along the length. So now in the first row, no, so we'll have the tube like this, correct? We'll have the tube, we'll have tank, and tubes like this. We can keep number of tubes like this. Clear? So if you keep 12 along here means this side, another side, this is the top of the tank, consider. So we have 2 length and 2 width. So 12 plus 12, 24. Here we, if we keep 6, no, if we keep 6 here, 6 plus 6, 12. So totally first row, no, first row we have 2 into 12, correct? Then 2 into 6, 24, 12. Okay, so together we will have first row 24 plus 12, 36 tubes will be available, correct? 24 plus 12, we will have 36 tubes, but we need to provide 62. So 62 minus 36, remaining 26 tubes are there to produce. So we go for second row. So second row, in second row, no, usually tubes are provided in this manner. So if we uh, keep the tubes in the first row like this, second row I can keep the tubes like this, correct? So what happened, the count will be lesser than the first row, so that 2 into 11, previously I have provided 12, no, now it will be 11. So 2 11s are 22. Similarly, in the along the width, no, previously I have kept 6, now I can keep only 5. So 2 into 5 is equal to 10. So together in the second row, 22 plus 10, 22 plus 10, I have put 32, correct? First row I have total 36 tubes, second row I have totally 32 tubes. So total tubes provided now along the length and width, the first row as well as second row, is 36 plus 32 is equal to 68 tubes. Okay, so for this again I have to find out edge spacing. Okay, so edge spacing, I have to leave some edge spacing, correct? So totally now see here, uh, 12 tubes are provided along the length. So for example, if I have 3 tubes, how many spacings are there? 2 spacing, correct? So now I have provided 12 means totally I am having 975, correct? Totally I am having 1000 mm, correct? 1000 mm minus tubes are provided in this space, 11 spacing will be there. 11 into 75 is equal to 175 mm is available at the edges. Both the edges means now 175 divided by 2. So 8 is 16, 15. So 0.5 mm, correct? So 87.5 mm is available at both the end along the length. This is for length. Okay, this is along the length of the tank. So edge spacing is 87.5 mm at both end, correct? Similarly for width. Okay, so total width is 500. I have provided 6 tubes, so I'll get 475 mm space, correct? So if I solve this, 6, no, then I'll get 6 tubes, so I'll get to 575 mm. So 125 mm. In both the cases, both the end means 125 by 2 and 5 mm. So along the length, both the edge I have 87.5 mm. Along the width at both the edges I am having 62.5 mm. Okay, thank you all.